last thing. We're building toward constructing the real numbers, and there's sort of a canonical way of doing that called Dedekind cuts, which I mentioned in the introduction. And there's a canonical book called Principles of Mathematical Analysis by Walter Rudin. And this is sort of like the famous example where he creates the real numbers using the Dedekind. I say Dedekind.
Some folks called it a sling blade. I call it a Kaiser blade.
Cuts. So before that in the book, when he's talking about the situation that we're talking about here, I've shown you sort of like, I think it's intuitive why what we're talking about is true, because the square root of 2 is not a rational number, which we proved. But he actually proves it. He goes a little further and proves that if there's if you have two sets with that such that square root of 2 is less than, or I'm sorry, 2 squared, p squared is less than 2, p squared is greater than 2. He actually proves that no matter what number in A you find, you can always find one bigger that's still that's still squared is less than 2. And at the same time, if that number is bigger than the square root of 2, you can always find one smaller. So I'm just going to show you that proof real quick, just to be formal about it. And it's some algebra, which is always good to look at. So the claim is that no matter what value of p you show me, I can always find another value q, such that q is bigger than p, and the q is still, and the q squared is still less than 2. No matter how close you get to p, I can always find one that's inside. And yet, on the other hand, that's when p squared is less than 2. If p squared is greater than 2, then I can always find a q that's less than p, but still q squared is greater than 2. Okay, so I think I can do it here. So whatever p you give me, we make q equals p minus p squared minus 2 over p plus 2, which is, so I'll just do the math real quick. So we have to find a common denominator. So p times p plus 2 over p plus 2 minus p squared minus 2 over p plus 2 equals p squared. So I think I can do this in one step. So this is p squared. So these cancel. This is 2p. And then what's left is plus 2 over p plus 2. Okay? And then starting with this, if we square q, we get 4p squared plus 8p plus 4 over p plus 2 squared. I know none of this is motivated yet. I'm going to show you where he gets it from in a second. And then he takes q squared minus 2 equals, so we have to subtract 2 from this side too. So we have p squared plus 8p plus 4 over p plus 2 squared. And then, again, we're going to multiply the top and the bottom by this. It gets a little tedious, but we have minus 2 times p squared plus 4p minus plus 4 over p plus 2 squared. So now, did I do that right? Yes. So this is p to the fourth. This is 4p squared minus 2p squared is 2p squared. And then minus 8p plus 8p, these cancel. And then, is that right? Oh, right. And then plus 4 and minus 8 is minus 4 over p plus 2 squared equals 2 times p squared minus 2 over p plus 2 squared. Okay, so the reason I just did this without justifying what we're doing is that he kind of does the same thing. And someone sometime did a lot of algebraic manipulations to make all this work. But basically what the point of all this is, we know that the definition in this A is p squared less than 2, b is p squared greater than 2. So if p squared is less than 2, then that means that p squared minus 2 is less than 0 in A. In other words, it's negative, right? That means that this is negative. Oh, I always forget to mention this. I'm going to put it at the bottom. And p is greater than 0. That's obviously not necessary. Okay. So we have that this is minus, this is positive. So we have, therefore, that it's p, but minus a negative is going to be bigger than that. So this shows us that q is greater than p, because we subtracted a minus number, so q is greater than p. That was the first thing we wanted to show. And then, if you come down here and you take q squared minus 2, so remember, we still need q to be q squared to be minus 2, to be less than 2. So if q squared is less than 2, then q squared minus 2 is less than 0 also, right? So this is q squared minus 2. We need to show that this is less than 0. Well, we know that p squared minus 2 is 0. This is still positive. Multiply that by 2, this is still negative. This whole thing's negative. That's what we needed to show. So we show that if p is in A, then we can find a q such that q is greater than p and q squared minus 2 is less than 0. So it means that it's in here somewhere. Now, the interesting thing, though, about these equations and why they're so messy is that what you're doing, you're finding one that works no matter what p is. So if, on the other hand, p is in B, so let's say that p is here, if we plug this in, then we're still going to get a q that's also in B. So in this case, if p squared is greater than 2, that means that p squared minus 2 is greater than 0. That means that p squared minus 2 is positive. This number is also much smaller than p, because if p squared equaled 2, it would be here. And so p squared minus 2 is just a little bit, it's this is the difference between p and the barrier. So this number is much smaller than p. So it's going to be smaller than p, but still bigger than 0. So we've shown here that 0 is less than q is less than p. And now we just have to show that q is still bigger than, that q squared is bigger than 2. Well, so again, q squared minus 2 equals this. In this case, this is positive. We already showed that. This is still positive. That means this whole thing is positive. So we have that q squared minus 2 is greater than 0. Therefore, q squared is greater than 2. So that's just to show you that indeed A has no smallest number, B has no biggest number, and yet the barrier is not there in the middle. So what have we shown? It's important to remember that these gaps aren't big gaps. They're not like the integer gaps where you can drive a truck through them, where the integers are mostly space and then there's just a number once in a while. Q is the opposite. Rationals are the opposite of that. You can, no matter how close together they are, you can always find another number in between them. You can get infinitely small, infinitely close together, and still always find another between them. Because if you have two rationals such that R is less than S, you can always find a number halfway between. Just take the average. So R is always less than R plus S divided by 2 is less than S, right? That's just the average of these two. It's going to be halfway between. No matter what, these are all rationals. We never left the rationals. Always there's a smaller one. And yet, we still have sets where there's no least upper bound in Q and no greater lower bound in Q. We can describe this boundary, but it's not actually in the rationals. So we've demonstrated that there are gaps. Even though these numbers are infinitely close together, there are still nonetheless gaps between them. And the real number system fills these gaps. And that's what we're going to do starting with the next video.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.